Hi guys, here back again trying to solve the remaining questions on Chapter 2 of the Art of Electronics. Previously we've designed a differential amplifier with certain gain that we were supposed to achieve, and we have designed and tested it, and it's met all the requirements the question asked us. Now let's go ahead and design one of the applications of differential amplifiers in real circuits, which is the variable gain amplifier. So let's go ahead and start question 6 and find out how we can design this variable gain amplifier. Question 6 says, in this problem you will ultimately design an amplifier whose gain is controlled by an externally applied voltage. In Chapter 3 you will see how to do the same thing with FETs. Part A says, begin by designing a long-tail pair differential amplifier with emitter current source and no emitter resistors, which is undegenerated. Use plus or minus 15 volt supplies. Set IC of each transistor at 1 milliamp and use RC equals 1 kiloohms. Calculate the voltage gain from a single-ended input, other input grounded, to a single-ended output. And Part B says, now modify the circuit so that an externally applied voltage controls the emitter current source. Give an approximate formula for the gain of the gain as a function of controlling voltage. So the one in bracket is basically telling us what the flaw of such a design is. So let's go ahead and read it. In real circuit, you might arrange a second set of voltage controlled current sources to cancel the quiescent point shift that a gain change produce in this circuit, or a differential input second stage could be added to your circuit. So basically it's telling us that if we modify the emitter current source to change the gain of the differential amplifier we'll be designing, there will be a quiescent voltage at the collectors of both of the differential transistors, which will ultimately shift the operating point and causing basically a shift in operating point, which is not desirable. So because of that, then we can include either as suggested a voltage controlled current sources to cancel the quiescent point shift, or include a second stage differential amplifier which will cancel the common mode, because the shift will be equal on both transistors. Then it will be like a common mode input to the second stage, which will be ignored by a second set of differential amplifier. So let's see how we can design the first stage first, and I'll show you how to basically remove the flaw of the amplifier. So the amplifier, I have designed it completely with the required modification to cancel the quiescent point shift, which the schematic is shown here. As you can see, we have we'll go ahead and design each component in this video, but this is to give you a preview of what we're trying to achieve on this video. Basically we have a first stage differential amplifier which will be able to control the current source here, but thereby will be modifying the current that flows through these two transistors, the quiescent current, which will be able to modify the gain of the amplifier. And because when we modify the current in these two branches, the drop here, which is the collector voltage of these two transistors, will shift up or down depending how we're changing this current. That will cause undesirable effect, because basically that's the quiescent point shift, and that is cancelled, as you can see, by a second set of differential amplifier which has a fixed gain, which will be able to remove the quiescent point shift that we have in this stage. So for the moment though, let's go ahead and design this part, which is basically what we're asked at the moment, which will have a voltage controlled current source here, which will ultimately modify the gain of this amplifier. So I have shown a similar design on my previous video of how to design this part, the current source part, for to allow certain amount of current to sink from the differential amplifier and to select these resistors. But for our case, for this question, we're given this resistor and this resistor, so we don't have to design that part. Now what we'll need to do is basically design the current source and also find the overall gain as a function of the controlling voltage, which in this case will be VC, which is this point here. The book suggests us to use a second DC source here instead of using deriving this voltage, this controlling voltage, from the existing power supply that we're using from the plus or minus 15 volts. But usually in a circuit design, you're always trying to minimize the use of power supplies, so I have gone ahead and designed it this way. I'm not going to include a second, although I have plenty of power supplies here to use. I will basically ultimately derive the voltage from my already present voltage here. So I'm not going to include an external voltage to control this current source. So let's go ahead and design this part really quick. So as told in the question, we're told this is 1K, the two collector resistors, and the two matched transistors that we're supposed to use for our differential amplifier, and no emitter resistor here for degeneration because it will be undegenerated, so that our gain will be directly proportional to the current that's flowing through these two transistors, and our current source to control the current, which will modify the gain of the amplifier. And we're told to use, as I mentioned here, an externally applied voltage source to control, so if we call this VC, to control the current flow through this transistor. But like I showed you on my final circuit, I'm not going to use this for ease of minimization, because in a circuit design you're always trying to minimize the amount of voltage sources that your circuit uses. So what I'll do is I will only use voltages that are already present in the circuit. So this is my plus 15 volts, this is my minus 15 volts, and we're told this will be grounded, and this is where we'll apply our signal. My signal has a 50 ohm source impedance, and to balance the two inputs, I will include a 50 ohm resistor to ground there too. So now what do we have? Now what we need to do is we're going to tap this from a potentiometer that would allow us to modify the base voltage of this transistor, which we will derive from a potential divider. This is what we'll use. And we have to determine RCS here, the current determining resistor. Here I'm going to call this one R1, and I'm going to call this R2. R2 is I selected it as 10 kilo ohms, so that's fixed because it will be variable resistor. So I fixed it to 10K. I have selected 10K, so I have to design R1 and RCS. So the first thing to do is, this is where our output will take our output, right? This is where our differential output is going to be, right? From here to here, right? That's our differential output. So what we have to do is we have to consider this voltage. Remember, in order for this current source to operate as a current source, we have to make sure that we don't saturate this transistor, so that we have a good relationship between base current and emitter current and collector current, which is basically between base current and collector current being beta, and between emitter current and collector current being alpha. So in order to maintain the linearity, which basically we need to operate in the in this part of the transistor curve, basically in the active region. We have to make sure this transistor doesn't go in saturation. So in order to do that, we know that this will be 0 volts. There will be a very small drop when we go up to here because the current will be very small here. So I'm going to assume this one is also at 0 volts. If that one is at 0 volts, then if this transistor is biased correctly, then this point will be minus 0.7 because of the VBE drop here. Same thing, we come this way, this source will be grounded, for all internship purposes when we're doing DC analysis, because this is an AC source. For DC analysis, it will be grounded, so this point will be close to 0 as well. Same thing, by the time we get here, will be minus 0.7. And if these two transistors are matched, which means their VBE will be very close to each other, then the current that flows through here will be balanced as well, which basically will be, at this point, the voltage, these two voltages will sum up to minus 0.7 basically by the time we get down here. So in order to not keep this transistor in saturation, what do we have to do? Then remember, we have to make sure that to be in the active region, in the active region, V, which is VCB, which is collector to base voltage, should always be greater than 0, right? For VCB greater than 0, then this transistor is always in the active region, depending what the base emitter voltage is, right? So if we know this is minus 0.7, then we definitely know this one needs to be a voltage that's less than minus 0.7, because if this is minus 0.7, then it's gonna be 0, which means this transistor is already in saturation. So we have to make sure this voltage is always below minus 0.7. So what I'll do is I'll fix it to minus 1.4, for example. If I do that, by the way, the potentiometer leg, the tapped output, the maximum voltage that we'll get here, the most positive voltage we'll get here is when this tap is right here, which is basically closer to ground, because if it goes down here, then we're turning off this base to emitter junction, because this is minus 15, and then this, if this tap goes lower and lower to this side, then it's going to approach minus 15, which means we are turning off this base to emitter junction, so which is good. So the highest positive voltage we'll get will be by when this tap is here. So this minus 1.4 will be by when this tap is here. When this tap is when this resistor is when this tap is all the way here, then I'm gonna make sure that my output is this voltage is minus 1.4. How do I do that? That's by selecting R1 properly, right? So what we'll do is we'll do a simple voltage divider. Remember, what we'll do is we'll ignore this base current for our design, and we'll set the condition that is necessary so that we are able to ignore this current. So by voltage divider, what do we have? We have these two resistors like this. We have R1 here. We have R2, which is this resistor, this potentiometer, the tapped leg being all the way to here. And we have minus 15 volts here, and we have 0 volts here. What do we want? As an output, we want minus 1.4. We said that we know R2 is 10K, so we can easily design R1. We know R1 easy from voltage divider. So what I'll do is I'll quickly calculate that and tell you what the value is. Just to show you the process how you can calculate this, just in case for people who are not following along, I will actually do the actual math how to derive this this resistor based on these voltage and this resistor value. So since our ground is here, then our voltage divider is going to be R1 divided by R1 plus R2 multiplied by minus 15 equals minus 1.4, right? So If you look at it, since our ground is from here, so we're looking like this. So if we do this, and we know that R1 is the one we're trying to find, R1 plus, we know R2 is 10K, and then the minuses cancel, so 1.4 over 15. So if we solve for R1, we'll get, okay, so as you can see, the answer is around 1K. So what I did was I selected R1 to be 1.2K to make sure that I don't get close to minus 0.7 at this point. So if this is slightly larger than 1K, then we'll drop a little more here, so we'll be below 0.7 quite a bit here by when the tap is here. So what I did was, in my circuit, I have selected R1 to be 1.2K. Okay, all right. So in order to use this voltage divider rule, because we ignored the base current, remember, because the transistor will be connected here, it will load the circuit. So in order to ignore the loading effect of the base current, we have to make sure that R1 parallel with R2, right? R1 parallel R2 should be much greater than the impedance looking into this. Remember, there's the transistor here, right? The transistor is like this, right? Well, there's the source, there's the RCS here, right? So looking into here, we have to make sure that the impedance should be a lot greater than the parallel combination of these two. So we know that R1 and R2 in parallel should be a lot less than the impedance looking into here, which is the impedance looking into the transistor right here, right? At this point, the impedance looking here. The impedance looking into here is what? Beta plus 1 multiplied by RCS, right? So what do we have? One condition is beta plus 1 multiplied by RCS, right? If we do this, then we'll make sure that the loading effects of the base current is ignored. This equation would allow us to design what RCS needs to be. So from this, we know the parallel combination of R1 and R2, which is around 1.07 kilo ohms, and we have to make sure, like I said, to ignore the base current here, we have to make sure that it's much less than beta plus 1 RCS. And the transistor I'm using, its lowest beta is 100. So what I'll do is I'll take that as 100. So I'm going to ignore the 1 since beta is a lot larger than 1. So I'm just going to take 100. So in electronics, much less than means 10 times less. So in this case, what I'll do is I'll just take it as 50 times less to just make sure that, we don't have any problem. So if we do that, then this becomes an equality. Then all we have to do is solve for RCS. So RCS equals, in this case, 50 multiplied by 1.07 kilo ohms divided by 100. So RCS that I selected is so I selected 510 ohms, which is basically a standard resistor. So as you can see, by doing this, then we're making sure that we can vary the current. Let's see how much the current can vary between. Remember, this tap is going to go from hitting this minus 15 all the way to what we designed it to be, to minus 1.4 volts, right? So from this, we can basically get the limits of the current that we are able to sink here, and also get the limits of the gain, because the gain will be directionally proportional to the current that's flowing through here. So the limits is V max, what I'll do is IC, I'm going to call this IC, right, which is the sum of this and this. IC will be the IC1, which will be when this voltage is at minus 1.4 is, it will go down by another 0.4 here, so it's going to be minus 1.4 minus 0.7, then divided, plus 15, which is on the other side of this resistor, divided by the resistor that we selected, which this one is 510. So this will be one of the extremes of the current, which is we get the highest current that we'll be getting flowing through here. So this comes out to be, so the two extremes of the current will be, the highest current will be able to sink through here will be 25 milliamps, and the smallest one will be 0 milliamps, because when this stop is right here, it's hitting minus 15, so minus 15 going to here to minus 15, so this base emitter junction is turned off, so we'll get 0. So as you can see, the current is a lot, 25 milliamps if we select 510, 25 milliamps. 25 milliamps coming through here means through here 25 milliamps divided by 2 is flowing, right? Because this will be, you know, each will be sinking similar amount. So by the time we hit here 25 milliamps divided by 2, what is this voltage going to be? So this voltage VC at that point, when this stop of this resistor is here, 25 milliamps divided by 2 is flowing through here. So this point, which I'll call VC, is 15 from here minus this collector resistor which were given in the question multiplied by 25 milliamps divided by 2, which is equal to, which is 2.5 volts. So, you know, as you can see, the voltage here will hit 2.5 volts at our maximum collector current that we're flowing. I don't want it to go down all the way to 2.5 volts, so what I have done is I have just doubled this the value of this RCS to 1.2 kilo ohms. So I have doubled it just to reduce the amount of current that's flowing. So instead of now 25 milliamps divided by 2 that will get, which is around 12.5, we'll instead get you know, half of that, so around 6 milliamps or something, right? So the maximum current will be 6 milliamps flowing through here, each of this basically. That's what I did, and it won't affect the calculation that we've done here, because we've taken a liberty of such, you know, like 50 ohm time, like, sorry, 50 times here. So all we have done is we had, you know, with this factor becomes 25. That's what I did to get that resistor, so it's okay. So we still are able to ignore the base current compared to the current that flows through here, so we're still good. So I've made sure that in my design RCS is 1.2 kilo ohms to reduce the current. I didn't want this voltage to swing down all the way to 2.5 volts. Okay, all right, so now, as the question suggested, now that we have designed our controlling voltage, which will vary from minus 50 all the way to minus 1.4, let's see what our gain is. What are our gain extremes? When the step is here, which is minus 15, then our gain is 0 because no current is flowing through here. So our gain is going to vary. G, I'm going to call it, our gain here is going to vary between 0 when this transistor is off to when this step is all the way here, minus 1.4, to that gain. So what we'll do is we'll see what the highest gain that we'll be able to get based on this value. So let's go ahead. Okay, the completed design variable gain amplifier design is shown with all the calculated values in the circuit. And now what we have to do is, as we said, our gain is going to vary when this tap of this resistor is all the way to here, which is 0 because this transistor is off. So the gain, I'm going to call it, which I think I called it G. So this will be G. The gain of this amplifier, the overall gain, is, you know, voltage gain. So GV is less than 0 when this transistor is off, and to a maximum value. What is that maximum value? So let's calculate it here. So we know that the current of such an amplifier, which has basically doesn't have any emitter degeneration, such an amplifier is just like a normal common emitter amplifier. So its gain is given by, let's call it AV, its gain is given by GM, right? GM, it's given by minus GM times the collector resistor here. So this is RC, GM RC, GM being the transconductance of the amplifier at the current that it's flowing. So, but because now we're using this differential amplifier, basically this voltage will be inputted into both sides of this differential amplifier, so half of it will be applied here and the negative half of that will be applied here. Then the single-ended differential gain is going to be positive GM RC divided by 2. So that's the gain, right? We can derive this, but I don't think it's necessary to do it here because we're doing a design. So if you want to prove to yourself how to get this gain, search differential amplifier gain in YouTube and you'll be able to get. And also it's also given by AV equals RC divided by 2 times the dynamic resistance of this transistor at the current, at the emitter current that we get. But so these two equations are the same, so they're basically saying the same thing. So we'll use this since this will give us directly the gain. So AV, then if I put it down here, the maximum gain, which I'll call it max, is, we said that it's given by GM RC divided by 2. We know that GM is given by IC divided by VT, right? The terminal voltage. RC divided by 2. So the VT will come down. So AV max will be given by IC RC divided by 2 VT. And we know all these parameters. We know the current. What's the current? Sorry, let's put that on the shot. What's the current? The current is the current that's flowing through here, which basically the current, you know, this current here, half of it basically, because they'll both add up here. So we know, we said that the maximum gain we'll get is when this stop is hitting this, and we designed this point to be 1 minus 0.4, right? So if this is minus 1.4, this goes down to minus 1.4 minus 0.7 plus 15 divided by 1.2k, which I have shown you before. You know, the current, we have already designed this current. So this current, which I'll call IE, is basically going to be twice amount of IC. So in this case, what I'll do is this IE, which I'll put here as a prime like that, 2 times IE prime like that, right? Sorry, it should be half, right? Because IC is half of that, right? This current, which our gain depends, is half of this current. So it should be IE divided by 2, right? RC divided by 2 VT. So this becomes 4 VT, right? So if we write this nicely here, IE prime, which is the current source current, multiplied by RC, I'm giving you the overall gain, 4 VT. That's what it's going to be. So if we put all these values in, we have calculated IE in the previous video, right? Remember, we said it was 25 milliamps for 510 ohm resistor, but for 1.2 kilo ohms it's going to be close to half of that. So if I will calculate and tell you the actual value. So that is going to be, so the maximum gain is 103. So basically, if you take a look at the parameters I put in, the 10.75 milliamps is the current passing through this transistor, through this current source, which will be twice the amount that's passing through here, right? Which, because these two are added, so this current is twice the amount of this current. So based on that, we're gonna, and then we put the collector resistor we're given as 1K. We put the 4 constant and the 26 millivolts of the thermal voltage at 25 degrees centigrade. We get the maximum gain to be 103. So we should be able to vary the gain of this amplifier. So I'm gonna just write it here, from 0 all the way to 103. let's see if we can verify this. One more thing I would like to derive here is, while we are at it, is where we're told what is the gain of this amplifier as a function of the voltage here. We're told the controlling voltage, which will be VC. So let's derive that. So the derivation of the voltage is, the voltage gain as a function of the controlling voltage VC is, we're going to start from this one, which we have derived already, and we know IE is just, IE prime is this current here. So this current depends on VC, so it's very easy. So if we do this, IE is basically VC minus VBE of this transistor divided by this RCS, which I should include here, RCS. That is the controlling voltage. So IE then becomes, so if I include it here, sorry for the shakiness, VC minus VBE divided by RCS, which we have here, multiplied by RC divided by 4VT. So the gain as a function of the controlling voltage, so I'm going to call it AV as a function of VC, is equal to, so if you take a look, it's going to be VC minus VBE multiplied by RC divided by 4VT RCS. This is the approximate, actually this is not approximate, this is the proper gain as a function of the controlling voltage, a function of this controlling voltage. So this is the derivation for the gain. So now let's go ahead and verify some of our calculation that I've done on the bench. As you can see, I have built the circuit, but this circuit is the original circuit which I showed you here, which also includes the second stage differential amplifier, which helps us to cancel the common mode shift of this amplifier. So what I'll do is I'll ignore this part and I'll just do the measurements here. So let's go ahead and do the measurements quick. Okay, so time for the practical side of circuit design. Let's see if we what we have calculated, and in our calculations, let's see if it matches with the built-in circuit basically. So I have set up monitoring quite a few points on my circuit. So I have this this meter is measuring the voltage at the base of the current source transistor with respect to ground. So that would be this meter here. So at this right moment, this voltage is minus 2.336. And also this meter here is measuring, this meter here, yeah, it's measuring the voltage across the, basically across this 1.2k resistor, which basically sets our current for the differential amplifier. Basically it's our biasing for this to differential amplifier. So that meter is measuring this current. And just to recap, when I derived the voltage gain as a function of the controlling voltage, I forgot to include the plus 15 volts here. So make sure to include the plus 15 volts, which is basically this point here, these minus 15 volts here, because the current that flows is into this rail here, so we have to make sure to include that voltage. So if you noticed when I derived this about missing this plus 15, kudos to you. But just to make sure that the actual overall transfer function between the control voltage and the gain of the amplifier is this equation here. So make sure to include the plus 15 here. Okay, so now let's continue. This meter is measuring the collector of this side of the differential amplifier, and this meter here measuring the other side of the collector of the differential amplifier. As you can see, there's a bit of mismatch right now, so there isn't the same amount of current flowing through the two of this transistors, because my matching of these two transistors is not 100% perfect. So because of that, one is slightly passing more current than the other side. The reason why that's happening is because I don't have the emitter degeneration resistor here, so the matching of this transistor becomes very critical because we don't have the emitter degeneration resistor. But if we had emitter degeneration resistor, the matching of the collector voltages could have been close. But as you can see, even though I tried to match the two transistors, this is the best I could do. Okay, so right now we're passing slightly more than 10 milliamps of current, because remember, I'm measuring that voltage, the 12 volts here, and as you can see, it's 1.2k. So 12 volts divided by 1.2k, that's 10 milliamps. So we're passing 5 milliamps through here, another 5 milliamps through here, and as you can see, the this meter here, which is basically measuring exactly this voltage here, is at minus 2.275. And as you can see, I'm using the potentiometer, the 10K potentiometer that we're going to use to tune the control voltage, which controls our gain, is here. And as you can see, it's not turned all the way, basically it's not turned all the way up, so that's why we're getting slightly below. So what I'll do is I will dial this meter, this potentiometer here, and observe what happens to the control voltage. So as you can see, I'm able to vary the control voltage. So this is the minimum it can go. So as you can see, I have turned it enough, so that's the minimum it can go. And remember, we designed for minus 1.4, and as you can see, we're getting minus 1.45, so very close to our design the design specification that we did in order to control the voltage, in order to control the gain of this amplifier. And as you can see right now, this tap here is all the way here, so the 10K is completely in series with this resistor basically. Okay, and remember, what did we say? The gain, we calculated the gain of the amplifier at when our tap is all the way here, depending on the current that we did. We said it was what, 103. So if we use our gain equation, because now we know all our components, as a function of VC is, VC right now, what are we measuring? Minus 1.45, right? So let's put that here and calculate, and we're gonna verify the gain based on that. 45 minus VBE of the transistor, I'm just gonna take it as 0.7 plus 15 multiplied by RC. RC is 1K, which we're given, divided by 4 times 26 millivolts. Sorry, let's put that on the shot. Millivolts multiplied by RCS, which we have designed it to be 1.2K. If we do this and do the calculation, let's see what we get. We'll get exactly 103, which we already verified from prior calculations. So we're going to get around 103. So let's take a look what our gain is. So here is the signal. This green waveform, which is on channel 1, this green waveform is on channel 1. I'm monitoring it here. That's the input signal. So I'm putting in right now 37.2 millivolts. And the blue waveform is the output which is monitored right at this point here. So it's in phase with it because I'm taking it from here. So, and what am I getting? So my gain is going to be the 3.52 volts divided by the 37.2 millivolts that I'm injecting. It's slightly less than 100, as you can see. So if we actually do the actual calculation here, so let's punch that in our calculator. So I read 3.52 divided by 37.2 of millivolts that I'm putting in. There you go. Our gain is 94.6. So at the current that we're monitoring right now, which is basically right here across the 1.2k ohm resistor, so that is around this is slightly over 10 milliamps, which will be flowing in here, slightly less than 10 milliamps, and which basically divides equally between these two. And so based on that calculation, our gain came out to be, as you can see if we can focus that, 94.6, but our calculated was 103. So depending on the resistance tolerances on the resistors and like the mismatch on the transistors, and I say that our calculation is very close, which closely matches our measured data, as you can see. So now I will demonstrate clearly right now how this variable gain amplifier works. So let's just put these meters on again. So now see if I can put everything in one shot so you can see how the variable gain amplifier works. And so take a look. This meter, this small meter here on my right hand side, is measuring the control voltage. Remember, this is the control voltage. This is the collector output of one of the legs of the differential amplifier. So basically this is the quiescent shift that the book was talking about, which by modifying the current, that voltage will change. This one is also measuring the other side of the collector voltage of that differential amplifier, and this is the voltage across the 1.2 kilo ohm current source that we designed. This one is monitoring the voltage across it. So this one will be directly proportional. The voltage across here will be directly proportional to the current across the 1.2 kilo ohm resistor, which determines our current. So let's take a look. So if I put this on the same shot, so if I vary this, as you can see, take a look, the gain, see, I can control the gain. So if I zoom in closer to here, take a look, I can control the gain. So the gain is, this is completely off, meaning this is completely off. You can see my control voltage is minus 15 because this tap of this potentiometer is all the way here, so it turns off this base emitter junction, so we don't have any current flowing, so we have no gain. And as you can see, the voltage across the 1.2 kilo ohm resistor becomes 0 because the base emitter junction of the current source is turned off, and the collector of output of the differential amplifier goes all the way to 15 volts, right? Because if you take a look here, this is where I'm measuring, these 2 points I'm measuring, and this is 15 right now because no current is flowing through here. So VCC just appears, which is 15 volts, appears right here and right here, as you can see. Both meters, 15.013, 15.014, as you can see. So if we go back now, demonstrate this. So what I'm doing is I'm just controlling the gain of the amplifier. So by twisting this, I'm controlling the gain. So you can see that's the control voltage. Take a look at it as it gets varied, and the gain gets varied, as you can see. So 0. The reason you see the thing shift up a bit is because of the scope input where I'm measuring. It's AC coupled, and because it's AC coupled, the capacitor is charging up because of the quiescent shift, right? As you can see, because of the current changes, the quiescent point gets changed, and as you can see, you know, it affects the quiescent point. But as you can see, I can vary it. So this is the maximum gain we get and minimum gain. Okay, so now we have demonstrated completely the operation of variable gain amplifier by using differential amplifiers. Basically, we can control the gain of this amplifier by controlling the current that goes through the current source, which means, you know, the current sink here. By controlling its current using this voltage here, we are able to control the gain of this amplifier. This amplifier can be used in a lot of applications, such as such as in communication, for example, where you need to modulate a carrier signal by like an auto frequency source, which I will demonstrate on my next video, the application of this variable gain amplifier. And also it can be used in AGC type circuits, automatic gain control circuits. For example, you could use it in automatic volume control in a power amplifier, depending on the, you know, the input of the signal. You can sense that, and you can vary the control voltage here, and you'll be able to control the gain of the amplifier, which means you can control the volume of the amplifier. So many uses for automatic variable gain amplifier, I mean. So that's basically the operation of a variable gain amplifier. One thing I'd like to demonstrate before I finish, I know this video is long, is how to remove the quiescent voltage shift. As you can see, as I vary that potentiometer, which varies the control voltage, you can see the quiescent point getting shifted. So what I will do now is I'll use the circuit I designed earlier. So what I will do is I'll put a second set of differential amplifier, which will cancel the common mode input from these two, right? Because this differential amplifier only amplifies the variation in voltage from these two, right? So what I'll do is I will pass it to the second stage, which I've built here. This is the second stage here. The second stage here, and we'll be able to see the output voltage from this and this. And I will actually take the difference, these two. I'll use a math waveform in the scope to give me the differential voltage output, and we'll be able to see that the quiescent shift, as you can see, where there's like DC offset that you see because of the quiescent shift, that is not going to exist. So we'll be able to cancel that quiescent point shift using a second stage differential amplifier. So let me set that up, and we'll do that demonstration, and we'll call it a day. Okay, so I have set up my second stage differential amplifier that I will use to cancel the quiescent shift because of the change in current through these two collector the collector currents of these two transistors. So I'll use my second stage to remove that basically the common mode voltage using a second stage differential amplifier. So let's take a look. So as you can see right now, our gain is 0 because you can see the control voltage is right at the end. So the control voltage is all the way here, so minus 15, so that's why it's off. So if I increase control voltage to the positive direction, as you can see, there you go. So I go all the way almost to clipping. So there you go. So I go all the way to clipping, and you can see I'm hitting the rails, 15 volts, 15 volts. And if I go back down, I can vary the gain. So the gain of the amplifier can be all the way from 0 all the way to the maximum, as you can see. Now, because we have a second stage, the gain is not going to be, the maximum gain is not going to be 103 that we calculated. It's going to be a lot more than, because the second stage has also its own gain, so which we're not going to bother to try to calculate right now. But yeah, so as you can see, I can vary the gain on both ends of this, and then you can see there's no DC offset that noticeable on the waveform. You can see it just nicely varies from minimum to maximum. There's no DC offset because the second stage differential amplifier is canceling the common mode input from the first stage, right? So we don't have to worry about that because we're using a second stage differential amplifier, allowing us to compensate for the quiescent shift, the quiescent point shift, as you can see. And the matching on the transistors is decent. As I vary the gain, as you can see, there's slight shift in quiescent voltage of the two second stage differential amplifier, but not as bad as the first one, as you can see. Okay, and you can see that. And remember, this one is monitoring the current across the current source of the first stage, which tells us what our gain is. So you can see slight shift in quiescent point, but not terrible. So now what I'll do is I'll set up my scope to measure the differential voltage, basically from here, the difference of these two. That will give us the full differential gain of the amplifier. So let's do that really quick. So what I'll do is I'll set up my math waveform to do okay, there we go. So what I'll do is now I'll turn off channel 1 and channel 2. We don't need them because we can monitor the difference. Okay, so now let's do this. So if we vary our gain, so let's take a look here, and we're gonna measure the peak-to-peak output of the difference of the two channels. Okay, so now let's take a look. Sorry. So let's take a look here. We can go all the way from 0, no gain, all the way to maximum gain until clipping, which is our power supply. So slightly lower than that. There we go. So get around 28 output. So this is how a variable gain amplifier is designed. So such an amplifier is very useful in a lot of applications. My next video we'll be able to see the application of such an amplifier to communications. Alright, I hope you enjoyed this video. I'll see you next time. Thank you.